Right now, in this very moment, roughly 92% of every atom in the observable universe is hydrogen. Not carbon, not oxygen, not iron or gold, or any of the exotic elements that fill the periodic table. Hydrogen, the simplest thing that exists. One proton, one electron, and nothing else. And almost all of the remaining 8%, helium. 2 protons, 2 neutrons, 2 electrons. Together, these two elements account for more than 99% of all the atomic matter that has ever existed. Every galaxy you have ever seen in a photograph, every nebula, every star, every gas cloud drifting between the spiral arms of the Milky Way, almost all of it is hydrogen and helium. And here is what should stop you in your tracks. None of it was always there. There was a time, not so terribly long ago on the cosmic clock, when not a single atom existed anywhere. No protons, no neutrons, no electrons bound to nuclei. There was only energy, a blinding, incomprehensible ocean of energy so dense and so hot that the very concept of matter had no meaning. And then, in a window of time so brief it would be over before you could blink, the universe performed the most extraordinary act of creation it would ever accomplish. It forged hydrogen and helium out of nothing but light and heat. And in doing so, it wrote a chemical recipe that would govern everything that followed for the next 13.8 billion years. This is the story of how that happened. This is the story of the first atoms. It is a story that stretches from the unimaginable heat of the earliest fractions of a second, when temperatures exceeded anything that exists in nature today by factors of trillions, all the way to a quiet, cooling universe some 380,000 years later, when the fog finally lifted and simple, neutral atoms drifted in the expanding darkness, waiting for gravity to pull them together into the first stars. It begins in a place that is not really a place, at a time that barely qualifies as time, in conditions so extreme that our mathematics starts to stutter and break down. It begins at the very edge of what physics can describe, and what happens between the beginning and the end is one of the most dramatic sequences of events in the entire history of the cosmos. To tell this story properly, we need to reckon with scales that defy human intuition. We will talk about temperatures so high that the numbers lose all meaning, about time intervals so short that they make the blink of an eye seem like an eternity, about densities so enormous that the entire observable universe, every galaxy and star and planet, was compressed into a volume smaller than a single atom. We will meet particles that no longer exist, forces that behave differently from anything we experience today, and physical processes so exotic that they can only be described in the abstract language of quantum field theory. And yet, somehow, the outcome of all this strangeness was simple. 2 elements, hydrogen and helium, the raw materials for everything. Forces split apart like branches cracking from a single tree, symmetries shattered, forever changing the character of reality. A strange, perfect liquid of quarks and gluons filled all of existence, a substance hotter than any stellar core, and smoother than any fluid ever measured in a laboratory. Matter and antimatter waged a war of mutual annihilation so total, so complete, that only one particle in every billion survived the carnage. Ghostly neutrinos, those almost weightless phantom particles that barely interact with anything, broke free from the crowd and vanished into the void, streaming silently outward, never to return. And then, in a frantic burst of nuclear fusion, lasting no more than about 20 minutes, starting roughly 3 minutes after the Big Bang, and ending by about the 20-minute mark, nearly all the helium that would ever exist was assembled, nucleus by nucleus, in a cosmic forge that stretched across the entirety of space. We know this happened. This is not a fable or a myth dressed in scientific language. We know it because we can still see the evidence. We can measure the proportions of hydrogen and helium in the most ancient, undisturbed corners of the universe, in primordial gas clouds that have never been processed through the interior of a star. And those proportions match, with remarkable precision, what our equations predict. We can detect the faint afterglow of the moment when the first atoms formed, a whisper of microwave radiation arriving from every direction in the sky, uniform to 1 part in 100,000, at a temperature of just 2.725 degrees above absolute zero. We can study the nuclear reactions in our laboratories, measure the cross-sections and rates, and plug those measurements into our cosmological models, and the predictions come out right. The story of the first atoms is one of the most thoroughly tested and confirmed narratives in all of science. And yet, it remains, in many ways, one of the most astonishing stories ever told. Think about what it means. It means that the chair you are sitting in, the air you are breathing, the water in your glass, the calcium in your bones, the iron in your blood, all of it traces its ancestry back to a moment when none of it existed. Not a single atom, just energy, just heat and light, compressed into a space smaller than the head of a pin, expanding at a rate that beggars the imagination. So let us go back. Let us go all the way back, past the stars and the galaxies and the great cosmic web, past the dark ages when no light shone anywhere, past the moment when the first atoms captured their first electrons, past the nuclear furnace of the first few minutes, past the annihilation of antimatter, past the quark-gluon plasma, past the separation of forces, past the era of inflation, all the way back to the very beginning, or as close to it as our physics allows us to reach. We will take this journey one epoch at a time, following the universe as it cools and transforms, watching matter emerge from energy step by step. And by the end, we will understand not just how hydrogen and helium were made, but why the universe is composed the way it is, and how a handful of nuclear reactions in the first 20 minutes of cosmic history set the stage for everything that would follow over the next 13.8 billion years. There is something deeply unsettling about the first fraction of a second after the Big Bang. Not because it was violent, although it was. Not because it was hot, although the temperatures involved are almost meaningless to state in human terms. What is unsettling is that our best theories of physics, the ones that have been tested and confirmed in particle accelerators and astronomical observations, simply stop working at a certain point. They reach a wall, and behind that wall lies a mystery that no one on Earth has yet solved. That wall has a name. It is called the Planck epoch, and it refers to the first unimaginably tiny sliver of time after the Big Bang, a span of approximately 10 to the negative 43 seconds. Written out, that is a decimal point followed by 42 zeros, and then a 1. It is a duration so short that the human mind cannot meaningfully grasp it. To put it in perspective, the entire current age of the universe, all 13.8 billion years of it, contains roughly 10 to the 60th Planck times. The Planck epoch is to 1 second what 1 second is to approximately 30 billion trillion years. It is the smallest meaningful unit of time that physics recognizes. During this epoch, the universe was compressed into a space smaller than the Planck length, roughly 10 to the negative 35 meters, which is about 100 billion times smaller than a proton. A proton, mind you, is already inconceivably small. It takes about 10 million protons lined up side by side to span the width of a single atom. And yet, the Planck length makes a proton look gargantuan by comparison. The temperature was on the order of 10 to 32 degrees, a number so enormous that all earthly comparisons collapse under its weight. The core of the sun, at roughly 15 million degrees, is utterly frigid by comparison. Not just cold, but a rounding error below the Planck temperature. And here is the key problem. At these scales, both quantum mechanics and general relativity, the two most successful and best tested theories in all of physics, are simultaneously important, and they fundamentally contradict each other. Quantum mechanics governs the behavior of the very small, the world of particles, wave functions, and probability amplitudes. General relativity governs gravity and the curvature of spacetime, the world of masses and distances, and the bending of light. In almost all practical situations, you need only one or the other. The electrons in your computer are governed by quantum mechanics. The orbit of the Earth around the Sun is governed by general relativity. The two theories have separate jurisdictions, and each works brilliantly within its own domain. But at the Planck scale, you need both at the same time, because the entire universe is squeezed into a volume so small that quantum effects dominate. And yet the gravitational forces are so intense that general relativity cannot be ignored. And when you try to combine them, the mathematics produces infinities and contradictions and nonsense. We call the hypothetical missing framework quantum gravity, and it remains one of the great unsolved problems in all of physics. String theory, loop quantum gravity, causal set theory, and a handful of other approaches have all attempted to fill this gap. But none has yet achieved the kind of definitive, experimentally confirmed success that would allow us to describe the Planck epoch with confidence. So we cannot say, with any real certainty, what the universe was doing during the Planck epoch. We do not know if spacetime itself existed in a recognizable form, or whether it was some foamy, fluctuating quantum structure, utterly unlike the smooth continuum we experience today. We do not know if the concept of temperature had any meaningful definition. We do not know if the four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were merged into a single unified superforce, as some grand unified theories suggest, or whether something else entirely was happening, something our current theories cannot even describe. This is not a failure of science. It is an honest acknowledgement of the limits of our current knowledge. The Planck epoch is the ultimate frontier, the boundary beyond which our physics cannot yet penetrate. It is a reminder that the universe is older than our understanding of it, and that there are questions so deep that they may require entirely new frameworks of thought to answer. Some physicists spend their entire careers working on these questions, developing the mathematical tools that might someday allow us to peer behind the blank wall and describe the very first instant of creation. Until that day arrives, the Planck epoch remains a mystery, the ultimate dark room at the beginning of time. What we can say is that at some point, the universe emerged from this incomprehensible state and entered a regime where known physics begins to apply. And the first milestone in that transition was the separation of gravity from the other three forces. This is believed to have occurred at approximately 10 to the negative 43 seconds, right at the boundary of the Planck epoch. From that moment, gravity became its own thing, curving space-time independently, while the other three forces remained temporarily merged in what physicists call the grand unified force. And then, almost immediately, something happened that would shape everything. At around 10 to the negative 36 seconds after the Big Bang, the universe entered a phase called cosmic inflation, in a span of time almost too brief to describe. Far shorter than the blink of an eye, shorter than any human experience can encompass, the universe expanded exponentially, growing by a factor of at least 10 to the 26th. Imagine a grain of sand suddenly stretching to the size of the observable universe, and you begin to approach the scale of what inflation accomplished. This was not an ordinary expansion. Ordinary expansion is what the universe does all the time, stretching gradually as dark energy pushes space apart. Inflation was something far more violent and strange. It was space itself inflating, doubling and doubling and doubling in size at a rate that outpaced light itself. Nothing was moving through space faster than light. That would violate special relativity. Instead, space itself was expanding so rapidly that 2 points that were practically touching before inflation began could end up separated by distances larger than the entire visible universe. The driving force behind inflation is believed to have been a quantum field called the inflaton field. In its initial state, the inflaton field stored an immense amount of energy, and this energy exerted a peculiar kind of negative pressure on the fabric of spacetime, a repulsive gravitational effect that drove the exponential expansion. Inflation solved several deep problems in cosmology that had troubled scientists for decades. The first was the horizon problem, the cosmic microwave background, the oldest light in the universe, looks almost perfectly uniform in every direction. Even in regions of the sky that are so far apart they could never have exchanged information or energy since the Big Bang. At least not in the standard non-inflationary cosmology. How could these disconnected regions have the same temperature to 1 part in 100,000 if they had never been in contact? Inflation answered this by proposing that all those regions were once in close contact before inflation, sharing the same temperature in a tiny primordial patch, and were only carried apart by the inflationary expansion. The second was the flatness problem. The geometry of the universe appears to be very nearly flat, meaning the average curvature of space is extremely close to zero. This requires a very specific balance between the energy density of the universe and its expansion rate. Without inflation, This balance would have had to be fine-tuned to an absurd degree in the initial conditions. Inflation naturally drives the universe toward flatness, just as inflating a balloon makes its surface appear flatter and flatter to an ant standing on it. The third was the monopole problem. Many particle physics theories predicted the existence of exotic objects called magnetic monopoles, isolated north or south magnetic poles, which should have been produced copiously in the extreme conditions of the early universe, but none have ever been observed. Inflation solves this by diluting any magnetic monopoles that might have formed before inflation to such fantastically low densities that we would never expect to encounter one. Inflation solved several deep problems in cosmology that had puzzled scientists for decades. It explained why the universe looks so remarkably uniform in every direction, even in regions that should never have been in contact with each other. It explained why the geometry of space appears to be flat, neither curved inward like a sphere, nor outward like a saddle. And it explained why we do not observe certain exotic objects, like magnetic monopoles, that many particle physics theories predicted should exist. But inflation also did something else, something profoundly important for our story, and indeed for the entire subsequent history of the cosmos. It took the tiny quantum fluctuations that existed in the pre-inflationary universe, microscopic ripples in the energy of the inflattened field and in the fabric of spacetime itself, and stretched them to cosmic proportions. These quantum fluctuations, ordinarily confined to scales far smaller than an atom, were magnified by the inflationary expansion to sizes spanning millions of light years. Frozen into the fabric of space during the inflationary expansion, these fluctuations became the seeds of all future structure. Every galaxy, every cluster of galaxies, every void and filament in the great cosmic web can be traced back to those primordial quantum ripples, magnified by inflation to macroscopic, cosmological proportions. Without inflation, or something very much like it, the universe would have no structure at all. It would be a featureless, uniform gas, expanding forever into nothingness. The fact that we exist, that galaxies and stars and planets exist, is a direct consequence of the inflationary stretching of quantum fluctuations in the first instant of cosmic time. This is one of the most profound and counterintuitive results in all of cosmology. The large-scale structure of the universe, the distribution of matter on scales of hundreds of millions of light years, ultimately traces its origin to the random quantum jitter of a field in the first 10 to the negative 32 seconds of existence. When inflation ended, at roughly 10 to the negative 32 seconds, the inflattened field decayed and released its stored energy into the universe in a process called reheating. This dumped a colossal amount of energy into the cosmos, filling it with an incredibly hot, incredibly dense plasma of fundamental particles and antiparticles, quarks, antiquarks, electrons, positrons, neutrinos, antineutrinos, gluons, photons, W and Z bosons, and Higgs bosons, all moving at or near the speed of light, colliding and annihilating and being recreated billions of times every second in a seething, chaotic broth of energy and matter. The temperature after reheating was extraordinary, estimated at somewhere between 10 to 25 and 10 to 27 degrees, depending on the specific model of inflation. It was at this moment, in a sense, that the Big Bang, as we commonly imagine it, truly began. The universe was now a roiling, expanding fireball, and the clock for our story had started ticking. From here on, physics is relatively well understood. We are in the domain of the standard model of particle physics, tested and confirmed at laboratories around the world. The mysteries of quantum gravity and the Planck epoch are behind us. What lies ahead is a sequence of transformations, each triggered by the cooling of the universe, each leaving a permanent mark on the composition and structure of the cosmos. The temperature immediately after inflation was staggering, on the order of 10 to 27 degrees or higher. At these energies, the universe was a domain where particle physics ruled, and the laws governing the smallest constituents of matter determined everything. In this era, the three remaining forces, electromagnetism, the strong nuclear force, and the weak nuclear force, were still not fully independent. The strong force is believed to have separated first, at around 10 to the negative 36 seconds, in what may have been the event that triggered inflation itself, though the details remain uncertain and model-dependent. After this separation, electromagnetism and the weak force remained merged into what physicists call the electroweak interaction. This unified electroweak force behaved very differently from either electromagnetism or the weak force as we know them today. The particles that carry the weak force, the W and Z bosons, were massless, just like the photon that carries the electromagnetic force. They all zipped around at the speed of light, interchangeable, indistinguishable in many of their behaviors, participating in reactions that would be impossible at the lower energies of the modern universe. This situation persisted until the universe was about 1/trillionth of a second old, roughly 10 to the negative 12 seconds after the Big Bang. At that point, the temperature had fallen to approximately 10 to 15 degrees, corresponding to an energy scale of about 160 billion electron volts. And at that threshold, one of the most important events in the history of the universe occurred. The electroweak symmetry broke. The mechanism responsible is called the Higgs mechanism, named after the British physicist Peter Higgs, who, along with several other theorists working independently in the 1960s, including Robert Brout and Francois Englert in Belgium, and Gerald Guralnick, Carl Hagen, and Tom Kibble in London, proposed the existence of a field that permeates all of space. In the extremely hot early universe, this field, the Higgs field, existed in a symmetric state. It was there, embedded in the structure of spacetime, but it had no preferred direction, no settled value. Think of a ball balanced perfectly on the peak of a Mexican hat-shaped hill. The hill is perfectly symmetric around the peak. As long as the temperature was high enough, the thermal energy of the particles kept the ball bouncing around near the top, maintaining the symmetry. But as the universe cooled below the critical threshold of roughly 160 billion electron volts, the ball could no longer maintain its perch. It rolled off the peak and settled into the valley, the brim of the hat, picking a particular direction. The Higgs field acquired what physicists call a vacuum expectation value, a non-zero value throughout all of space, and the electroweak symmetry was broken. On the 4th of July, 2012, physicists at CERN announced the discovery of the Higgs boson, the particle associated with the Higgs field, with a mass of approximately 125 billion electron volts. This discovery, one of the most anticipated and celebrated in the history of particle physics, confirmed that the Higgs mechanism was real. The field that gave mass to the fundamental particles was not a theoretical abstraction. It existed, and its effects had been measured. This was electroweak symmetry breaking, and its consequences were transformative. The W and Z bosons, previously massless and long-ranged, suddenly acquired mass. The W bosons became roughly 80 times as heavy as a proton. The Z boson became about 91 times as heavy. This mass made the weak force extremely short-ranged, operating only across distances smaller than an atomic nucleus. Meanwhile, the photon, the carrier of the electromagnetic force, remained massless, and electromagnetism retained its infinite range. In essence, the universe went from having 3 unified forces plus gravity to having 4 distinct forces, each with its own character, its own range, its own set of carrier particles. The physical laws that govern our everyday world, the laws of chemistry, electricity, and light, came into existence at this moment. Before electroweak symmetry breaking, those laws did not yet exist in their present form. The universe would not have been recognizable to us. But the Higgs mechanism did more than just give mass to the force-carrying bosons. It also gave mass to the fundamental fermions, the quarks and the leptons, which include electrons and neutrinos, through what are called Yukawa couplings. Before this moment, in a sense, nothing had the kind of mass we are familiar with. The quarks that would eventually build protons and neutrons had no intrinsic mass from the Higgs. After this transition, they did. The electron, which would one day orbit atomic nuclei to form complete atoms, gained its tiny but crucial mass. The universe had crossed a threshold. It now contains particles with the masses they carry to this day. And with these newly massive particles, the next dramatic chapter could begin. After the electroweak transition, the universe entered what cosmologists call the quark epoch. The temperature was still fantastically high, well above 10 to 12 degrees, and the dominant form of matter was a state that has no analogy in everyday experience. It was called the quark-gluon plasma. In our familiar world, quarks are never observed in isolation. They are always confined inside composite particles called hadrons, the most important of which are protons and neutrons. This confinement is enforced by the strong nuclear force, which is carried by particles called gluons. The name color in this context has nothing to do with visible light. It is a whimsical label that physicists gave to the quantum property, analogous to electric charge, that quarks carry and that the strong force acts upon. Just as electromagnetic forces act between electric charges, the strong force acts between color charges, which come in 3 varieties: red, green, and blue. All observable hadrons are color neutral, meaning the colors of their constituent quarks combine to produce a net color charge of 0, much as red, green, and blue light combine to produce white. The strong force has a peculiar and counterintuitive property that sets it apart from every other force in nature. Unlike gravity or electromagnetism, which weaken with distance, the strong force actually gets stronger as you try to pull two quarks apart. Attempting to separate quarks is something like stretching a rubber band. The farther you pull, the more energy you invest, until eventually the energy stored in the stretching becomes so great that it materializes as a new pair of quarks. A quark and an antiquark popping into existence from the vacuum, rather than allowing the originals to fly free. This phenomenon, called color confinement, is why isolated quarks do not exist in nature today. You can never peel a quark away from its companions. The universe will create new quarks to prevent it. But in the first microseconds after the Big Bang, the universe was so hot and so dense that this confinement was irrelevant. The quarks and gluons existed as a free-flowing plasma, unbound, interacting constantly, but never sticking together for long. Imagine a pot of soup so furiously boiling that no ingredient can hold its shape. The quark-gluon plasma was something like that, but far stranger when scientists at the relativistic heavy ion collider at Brookhaven National Laboratory in New York first recreated tiny droplets of quark-gluon plasma in the year 2000 by smashing gold nuclei together at nearly the speed of light. They expected it to behave like a gas. The logic seemed sound. Free particles at enormous temperatures should scatter and bounce around like molecules in a hot gas. But the quark-gluon plasma turned out to be nothing of the sort. It behaved like a liquid, and not just any liquid. It was the most perfect liquid ever observed, flowing with almost zero viscosity, less resistance to flow than any other substance ever measured by human instruments, at any scale, under any conditions. Physicists call this a nearly perfect fluid, meaning that its viscosity to entropy ratio approaches the theoretical minimum allowed by quantum mechanics. It moved collectively, like a single unified body, rather than as a collection of independent particles. The announcement was met with skepticism at first. Part of the difficulty was that scientists had not yet agreed on the precise criteria for confirming the creation of the quark-gluon plasma. As Barbara Jacek, a longtime RHIC researcher and physicist at the University of California, Berkeley, and Lawrence Berkeley National Laboratory, noted, different groups had different interpretations of the data. It took years of careful analysis and debate before the physics community reached consensus. But by the mid-2000s, the evidence was overwhelming. RHIC had recreated, in miniature, the substance that had filled the entire universe in its first millionths of a second. This was one of the great surprises in modern physics. The primordial substance of the universe, the material that existed when the cosmos was only a millionth of a second old, was an ultra-hot, nearly frictionless liquid of quarks and gluons. More recent experiments at CERN's Large Hadron Collider have confirmed and extended these findings. In late 2025, researchers in the CMS collaboration observed, for the first time, the clear signature of a quark creating a wake as it moved through the plasma. Something like a duck trailing ripples through water. This confirmed that the quark-gluon plasma truly behaved as a fluid, responding collectively to disturbances rather than scattering randomly. As the universe expanded and cooled, this perfect primordial liquid could not persist. At a temperature of roughly 2 trillion degrees, corresponding to an energy of about 150 and 70 million electron volts. The strong force asserted its confining grip. Quarks began to bind together into hadrons. This transition, called hadronization, or sometimes the QCD phase transition. QCD standing for quantum chromodynamics, the theory of the strong force, happened when the universe was approximately 10 to the negative 5 seconds old, roughly 10 microseconds after the Big Bang. The QCD phase transition is one of the most dramatic transformations in cosmic history, though it is often overlooked in popular accounts. Before this transition, the universe was a smooth, continuous liquid of quarks and gluons, where individual particle identities were essentially meaningless. After the transition, the liquid crystallized into a gas of distinct, composite particles, each with a definite identity and set of properties. It was something like water freezing into ice, except the physics was immeasurably more complex, and the process took place across the entire observable universe simultaneously. During hadronization, quarks are combined into groups. Up quarks paired with down quarks to form protons, each consisting of 2 up quarks and 1 down quark, and neutrons, each consisting of 1 up quark and 2 down quarks. A proton has a mass of approximately 938 million electron volts, and a neutron has a mass of approximately 939.6 million electron volts. Remarkably, the vast majority of this mass does not come from the quarks themselves. The up and down quarks have intrinsic masses of only a few million electron volts each, courtesy of the Higgs mechanism. The rest, more than 98% of the mass of a proton or neutron, comes from the energy of the strong force interactions binding the quarks together. A dramatic demonstration of Einstein's famous equivalence of mass and energy. The mass of your body, the mass of the Earth, the mass of every object you have ever touched is overwhelmingly not Higgs-generated mass. It is the energy of the strong force, frozen into the structure of protons and neutrons. Along with protons and neutrons came a bewildering zoo of other hadrons, including mesons, quark-antiquark pairs, such as pions and kaons, and more exotic combinations. But most of these were unstable and decayed almost immediately, within tiny fractions of a second, into lighter particles. What survived, what mattered for the future of the universe, were protons and neutrons. These are the building blocks of atomic nuclei, and they have now come into existence for the first time. But there was a problem, a very big problem. Alongside every proton, there was an antiproton. Alongside every neutron, an antineutron. The universe, it seemed, had created matter and antimatter in almost perfectly equal amounts. Antimatter is not science fiction. It is as real as the chair you sit in, as the ground beneath your feet. An antiproton has the same mass as a proton, the same spin, and the same magnitude of charge, but with the opposite sign. An antielectron, called a positron, is identical to an electron in every way except that it carries a positive charge instead of a negative one. Antimatter is, in a sense, a perfect mirror image of matter. It was first predicted theoretically by the British physicist Paul Dirac in 1928, and first observed experimentally in 1932, when Carl Anderson photographed a positron track in a cloud chamber at Caltech. And when a particle of matter meets its antimatter counterpart, they annihilate each other. Completely. Totally. Their combined mass is converted entirely into energy, into photons. High-energy gamma rays that streak away at the speed of light. Nothing is left behind. No remnant, no debris, no trace of the particles that were there a moment before. Just pure energy. The amount of energy released is enormous. Even a single gram of matter annihilating with a single gram of antimatter would release roughly the energy of the Hiroshima atomic bomb. Now imagine this happening on a cosmic scale, with every particle in the universe finding its counterpart and being destroyed. If the balance had been exactly perfect, every proton would have found an antiproton, every neutron an antineutron, and the mutual annihilation would have been total. The universe would contain nothing but light. No matter, no atoms, no stars, no planets, no life. Just an expanding sea of cooling radiation, dimming forever into emptiness. Obviously, that is not what happened. And the reason it did not happen is one of the deepest mysteries in all of physics. Somehow, in the early universe, the balance between matter and antimatter was not quite perfect. For every billion antimatter particles, there were approximately 1 billion and 1 matter particles. That tiny asymmetry, that one extra particle per billion, was the margin that saved us. It meant that when the great annihilation occurred, when matter and antimatter found each other and were destroyed in a blaze of gamma radiation, a small residue of matter remained. Everything you see in the universe today, every galaxy, every star, every atom in your body is descended from that minuscule surplus. The process that created this imbalance is called baryogenesis, and despite decades of searching, physicists do not fully understand how it happened. In 1967, the Soviet physicist Andrei Sakharov, better known to many as a dissident and human rights advocate, identified 3 conditions that any theory of baryogenesis must satisfy. First, there must be interactions that violate baryon number conservation, meaning processes that can create a net imbalance between particles and antiparticles. Second, certain symmetries of nature, specifically charge conjugation symmetry, called C, and the combined charge parity symmetry, called CP, must be violated. If these symmetries were perfect, then any process that favored matter would be exactly counterbalanced by a mirror process favoring antimatter, and no net surplus could arise. Third, these interactions must occur out of thermal equilibrium. In equilibrium, every process is balanced by its reverse, and no lasting asymmetry can develop. The standard model of particle physics does contain processes that satisfy all 3 of Sakharov's conditions. CP violation has been observed experimentally. First, in the decay of particles, called kaons in 1964 by James Cronin and Val Fitch at Brookhaven National Laboratory, a discovery that won them the 1980 Nobel Prize, and later in the decay of B mesons at the Babar experiment at SLAC and the Bell experiment in Japan. Baryon number violation occurs through exotic quantum tunneling processes called sphalerons, which are active at the high temperatures of the early universe. Sphalerons are not individual particle interactions, but rather collective transitions of the electroweak fields, involving the simultaneous creation or destruction of multiple quarks and leptons. They are fantastically rare at today's temperatures, but would have been frequent in the hot plasma of the electroweak epoch. And the expanding, cooling universe was certainly out of equilibrium. But here is the frustrating reality: the amount of CP violation in the Standard Model and the nature of the electroweak phase transition, as we currently understand it, appear to be far too small to generate the observed matter-antimatter asymmetry. The Standard Model predicts a surplus many orders of magnitude less than what is needed. Something beyond the Standard Model must have been at work. Some new particle, some new interaction, some new source of CP violation that we have not yet discovered. Various theories have been proposed. Some invoke extremely heavy particles that do not exist in today's universe, but could have been produced in the intense heat of the early cosmos. These particles might have decayed preferentially into matter over antimatter, seeding the asymmetry. Other theories invoke a mechanism called leptogenesis, in which the asymmetry first develops in the lepton sector, among particles like neutrinos and electrons, and is then partially transferred to the baryon sector through Sphalerin processes. Still others look to exotic phenomena connected to the electroweak phase transition itself, or to processes during or after inflation. The truth is, we do not know which mechanism was responsible. The origin of the matter-antimatter asymmetry remains one of the great open questions in physics and cosmology. It is a question whose answer may require new particles, new forces, or new principles that we have not yet imagined. But regardless of how it happened, the result was clear. By the time the Great Annihilation was over, perhaps a millionth of a second after the Big Bang, the universe had been purged of nearly all its antimatter. What remained was a hot, expanding plasma of protons, neutrons, electrons, photons, and neutrinos, along with a vast bath of radiation produced by the annihilation itself. For every surviving proton or neutron, there were approximately 1 billion photons. The universe was overwhelmingly dominated by light. If you could have somehow frozen the cosmos at that moment and taken an inventory, you would have found that its energy budget was almost entirely in radiation. Gamma rays, streaming in every direction, colliding and scattering, and filling every cubic centimeter of space with a blinding luminosity that no human eye or instrument could withstand. The surviving matter particles, the protons and neutrons and electrons that would eventually become every atom in every star and every planet, were a negligible impurity in that ocean of photons. A contamination, a rounding error, and yet that rounding error was everything. Without it, the universe would be nothing but an expanding bath of cooling radiation, forever empty, forever dark once the light redshifted below visible wavelengths. There would be no structures, no chemistry, no complexity of any kind. Just photons, stretching and cooling into the microwave range over billions of years, filling a featureless void. It is worth pausing to appreciate the scale of what had just occurred. The matter-antimatter annihilation was, by any measure, the most destructive event in the history of the cosmos. It erased roughly 99.9999999% of all the matter and antimatter that had been created during the quark epoch and hadronization. The energy released was staggering. It dwarfed the combined output of every star that would ever shine, every supernova that would ever detonate, every gamma ray burst that would ever flare across the sky. And yet, from the perspective of the universe's future, the annihilation was not a catastrophe, it was a purification. It burned away the antimatter and left behind a clean, radiation-dominated plasma in which the surviving protons and neutrons could begin the long process of assembling into nuclei and, eventually, atoms. The universe had passed through a fire, the most intense fire imaginable. And what emerged on the other side was the raw material for everything that would follow. Stars, galaxies, planets, oceans, organic molecules, and ultimately, consciousness itself. There's a strange and almost poetic symmetry to this. The matter that makes up your body, the atoms in your bones, blood, and brain, all of it exists because of that tiny asymmetry in the early universe. You are made from the leftovers of the greatest annihilation the cosmos has ever known. You are, in the most literal sense, a survivor of a catastrophe that destroyed 99.9999999% of everything, and it was into this radiation-drenched, photon-dominated environment that the next great transformation would unfold. When the universe was approximately 1 second old, its temperature had cooled to roughly 10 billion degrees. This is still extraordinarily hot by any terrestrial standard, about 600 times hotter than the core of the sun. But it represented a dramatic cooling from the conditions of the preceding microseconds. And at this temperature, something important happened. The neutrinos, those ghostly, nearly massless particles that interact with other matter only through the weak nuclear force and gravity, lost their grip on the rest of the cosmos. Neutrinos are among the strangest particles in nature, and understanding their behavior is essential to understanding how the primordial elements were forged. They carry no electric charge. They have almost no mass, though experiments over the past few decades have conclusively demonstrated that their mass is not exactly zero. Neutrinos oscillate between 3 different types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And this oscillation is only possible if they possess a small but non-zero mass. The exact mass is still unknown, but it is extraordinarily tiny, at least 500,000 times lighter than the electron, which is itself the lightest particle with measurable mass in everyday matter. Neutrinos interact with other matter only through the weak nuclear force and gravity, both of which are fantastically feeble at the energies and distances relevant to ordinary life. The result is that neutrinos are, for all practical purposes, invisible. They pass through matter as if it were not there. A neutrino produced in the core of the sun will fly through the sun's entire mass, roughly 2 billion metric tons of hydrogen and helium plasma, without interacting with a single particle. It then crosses the 93 million miles of interplanetary space to reach the Earth, and it passes through the entire planet, through the crust and mantle and iron core, and out the other side, without disturbing a single atom. Every second, roughly 65 billion neutrinos from the sun pass through every square centimeter of your skin, and you feel nothing. They pass through your body, through the floor beneath you, through the Earth itself, and continue on into the void of space. To detect a neutrino, you need an enormous detector and extraordinary patience. The Ice Cube Neutrino Observatory at the South Pole, for instance, uses a cubic kilometer of Antarctic ice, instrumented with thousands of photosensitive detectors, to catch the extremely rare interactions of high-energy neutrinos with water molecules. Even with a detector that massive, it catches only a handful of neutrino events per day. The Super Kamiokande detector in Japan, which played a key role in confirming neutrino oscillations, consists of a vast underground tank filled with 50,000 metric tons of ultrapure water. These are the scales required to study a particle that barely acknowledges the existence of matter. And yet, in the first second of the universe's life, neutrinos were not phantoms at all. They were central players, actively participating in the cosmic drama, colliding and interacting with other particles at a furious rate. Before this moment, neutrinos were in constant communication with the surrounding plasma. They collided with electrons, positrons, protons, and neutrons, frequently enough to maintain thermal equilibrium, meaning they shared the same temperature as everything else and participated actively in the cosmic drama. But the weak force, which governs these neutrino interactions, is inherently feeble compared to the electromagnetic and strong forces. Its effects drop off rapidly with decreasing energy. As the universe expanded and cooled, the rate at which neutrinos interacted with other particles declined steadily. Meanwhile, the rate at which the universe itself was expanding, driven by its enormous energy density, was also changing. At roughly 1 second, those two rates crossed. The weak interaction rate fell below the expansion rate, and the neutrinos decoupled. From that moment onward, the neutrinos streamed freely through the universe, no longer colliding with anything, no longer exchanging energy or information with the rest of the cosmic plasma. They became, in essence, invisible bystanders, and they have remained that way ever since. The cosmic neutrino background, as it is called, still fills the universe today, a relic population of primordial neutrinos at a temperature of approximately 1.95 degrees above absolute zero. We have never directly detected these neutrinos. Their energies are far too low for current technology. But their existence has been inferred through their subtle gravitational effects on the cosmic microwave background and on the formation of large-scale structure. Neutrino decoupling had a profound and direct consequence for the story of nucleosynthesis because it set the neutron-to-proton ratio. Before decoupling, the weak force maintained an equilibrium between protons and neutrons through reactions involving neutrinos, electrons, and positrons. Protons could transform into neutrons and vice versa. A neutron plus a positron could produce a proton plus an antineutrino. A proton plus an electron could produce a neutron plus a neutrino. These reactions and their reverses kept protons and neutrons in a constantly shifting balance, determined by their slight mass difference. A neutron is about 1.293 million electron volts, heavier than a proton, roughly 1/10 of 1% more massive. At very high temperatures, this mass difference is negligible compared to the thermal energy of the particles, and protons and neutrons exist in roughly equal numbers. But as the universe cooled toward the 1 million electron volt mark, the heavier neutrons became progressively more expensive to produce. Thermodynamically speaking, the Boltzmann factor, the exponential weighting that determines how likely a particle is to have a given energy, began to disfavor neutrons. By the time of neutrino decoupling, the neutron-to-proton ratio had fallen to approximately 1:5. There were about 5 protons for every neutron, and then the weak interactions froze out. The ratio was locked in, at least approximately. It would continue to change slowly because free neutrons are unstable. A neutron sitting by itself, unbound in any nucleus, will spontaneously decay into a proton, an electron, and an antineutrino with a mean lifetime of approximately 878 seconds, or roughly 14 minutes and 38 seconds, corresponding to a half-life of about 10 minutes and 13 seconds. So from the moment of weak force freeze-out onward, the supply of neutrons was dwindling. Every minute that passed, more neutrons decayed into protons, and the neutron-to-proton ratio crept lower. By the time nucleosynthesis actually began, a few minutes later, the ratio had fallen from 1:5 to approximately 1:7. This ratio, 1 neutron for every 7 protons, is one of the most consequential numbers in all of cosmology. It determines, almost entirely, how much helium the universe would produce. And the fact that our theoretical prediction of this ratio, derived from well-understood nuclear and particle physics, matches what we observe in the actual universe, is one of the most powerful pieces of evidence for the Big Bang model. This ratio, 1 neutron for every 7 protons, is one of the most consequential numbers in cosmology. It determines, almost entirely, how much helium the universe would produce, and the fact that our theoretical prediction of this ratio matches what we observe in the actual universe is one of the most powerful pieces of evidence for the Big Bang model. Shortly after neutrino decoupling, another annihilation event cleaned the house. The universe's temperature had fallen below the threshold needed to create electron-positron pairs from photon collisions. The existing positrons found their electron counterparts and annihilated, dumping their energy into the photon bath. This slightly heated the photons relative to the now decoupled neutrinos, establishing a temperature difference between the two populations that persists to this day. The photon temperature is slightly higher than the neutrino temperature by a factor related to the number of particle species present at the time, specifically the cube root of 11/4, which works out to approximately 1.4. Now the stage was set. The universe was a few seconds old, filled with protons, neutrons, electrons, photons, and freely streaming neutrinos. The neutrons were slowly decaying, tick by tick, and the clock was running. If something did not happen soon, if the neutrons were not captured into stable nuclei, they would all decay away, and the universe would be left with nothing but hydrogen. No helium, no lithium, just hydrogen. But something did happen. It just did not happen right away. And the reason for the delay is one of the most elegant bottlenecks in all of nature. To build helium, you first need to build deuterium. This is inescapable. Deuterium, sometimes called heavy hydrogen, consists of 1 proton and 1 neutron bound together. It is the simplest compound nucleus, the first rung on the ladder of nuclear complexity. Every reaction chain that leads to helium passes through deuterium. There is no shortcut. You cannot simply slam 2 protons and 2 neutrons together and get a helium-4 nucleus. the probability of such a four-body collision is vanishingly small. The path runs through intermediaries, and deuterium is the first and most important of them. The reaction that forms deuterium is straightforward. A proton and a neutron collide and stick together, releasing a gamma-ray photon in the process. This reaction begins occurring almost immediately, well before the first second is over. Deuterium nuclei are constantly being assembled. The problem is that they are also constantly being destroyed. The binding energy of deuterium is quite low, only about 2.22 million electron volts. In the context of nuclear physics, this is quite modest. Helium-4, by comparison, has a binding energy of about 28.3 million electron volts, more than 12 times greater. Deuterium's weak binding makes it fragile, easily disrupted by energetic photons in a process called photodisintegration. A gamma ray with energy exceeding 2.22 million electron volts can shatter a deuterium nucleus back into its constituent proton and neutron. And in the early universe, energetic photons were not in short supply. They were overwhelmingly abundant. For every proton or neutron in the cosmos, there were roughly 1 billion photons, a ratio that physicists call the baryon-to-photon ratio. And it is one of the most important numbers in cosmology, even when the average energy of those photons dropped below the deuterium binding threshold. The sheer, staggering number of photons meant that the high-energy tail of the thermal distribution, that small fraction of photons with energies far above the average, vastly outnumbered the baryons. Imagine a vast crowd of 1 billion people. And even if only 1 in 10,000 of them is throwing rocks, that still means 100,000 rocks are flying at any given moment. The few deuterium nuclei that managed to form were immediately bombarded by those high-energy tail photons and blown apart. It was like trying to build a sandcastle while standing in the path of a fire hose. Every time a proton and a neutron came together to form a deuterium nucleus, releasing a gamma-ray photon in the process, another photon from the surrounding radiation bath would come crashing in from some random direction and shatter the newly formed nucleus back into its separate components. Build, destroy, build, destroy. Over and over, billions of times per second, in every cubic centimeter of the expanding universe. This is the deuterium bottleneck. It is a traffic jam at the very first step of nucleosynthesis, and it holds up the entire process for several minutes, even though the average temperature of the universe dropped below the binding energy of deuterium relatively early. The sheer number of photons meant that even the rare high-energy tail of the photon distribution, the small percentage of photons with energies far above the average, was more than sufficient to destroy deuterium as fast as it formed. Only when the temperature fell to about 700 million degrees, corresponding to an energy of roughly 0.06 million electron volts, roughly 37 times lower than the deuterium binding energy, did the photon bath finally become gentle enough to let deuterium survive. This happened approximately 3 minutes after the Big Bang. The deuterium bottleneck broke, and all at once, a frenzy of nuclear reactions began. The neutrons had been waiting, slowly decaying, their numbers dwindling with each passing moment. By the time the bottleneck cleared, the neutron-to-proton ratio had dropped from 1 to 5 to approximately 1 to 7. Roughly 1 out of every 8 nucleons, counting protons and neutrons together, was a neutron. And now, finally, those neutrons could be put to use. What followed was a burst of nuclear activity, unlike anything the universe has seen since. It lasted roughly 17 minutes, from about 3 minutes to about 20 minutes after the Big Bang. And in that narrow window, the lightest elements were forged. The process was sequential, a chain of nuclear reactions, each one building on the last. It began with the formation of deuterium, a proton and a neutron combining into a deuterium nucleus plus a gamma-ray photon. Once stable deuterium accumulated, it served as the feedstock for everything that followed. The reaction network branched out rapidly. Deuterium nuclei collided with protons to form helium-3, an isotope of helium containing 2 protons and 1 neutron, plus a gamma-ray photon. Deuterium nuclei collided with neutrons to form tritium, or hydrogen-3, which contains 1 proton and 2 neutrons, again releasing energy. Deuterium nuclei also collided with other deuterium nuclei in 2 possible reaction channels, one producing helium-3 plus a neutron, the other producing tritium plus a proton. These deuterium-deuterium reactions were actually among the fastest and most important in the network, because deuterium, once it began accumulating, was very reactive, and then the critical reactions occurred. Tritium plus deuterium fused to produce helium-4 plus a free neutron. Helium-3 plus a neutron produced tritium plus a proton, or alternatively, helium-3 plus deuterium produced helium-4 plus a proton. Multiple pathways all converged on the same destination, helium-4. It was a funnel, a gravitational attractor in the space of nuclear possibilities, drawing nearly all the available nuclear material toward the most stable light nucleus. Helium-4 is extraordinarily tightly bound. Its binding energy per nucleon is much higher than that of any other light nucleus, which means that once a helium-4 nucleus forms, it is very difficult to break apart. This stability made helium-4 the dominant product of Big Bang nucleosynthesis. Nearly every available neutron ended up inside a helium-4 nucleus. The whole process happened in a precise sequence determined by the temperature and density of the expanding universe. The earliest reactions, those involving the most abundant and reactive species, proceeded first. As the temperature continued to fall and the universe became more dilute, only the fastest reactions could keep pace with the expansion. Slower reactions, including those that might have produced heavier elements, simply ran out of time. The universe was a factory, but it was a factory that was shutting down even as it ran, its fuel being diluted by the relentless expansion of space. The arithmetic that determines the final helium abundance is elegant and surprisingly simple. At the time nucleosynthesis began, there was approximately 1 neutron for every 7 protons. That gives a total of 8 nucleons, of which 2 are neutrons. A helium-4 nucleus requires exactly 2 neutrons and 2 protons. So those 2 neutrons each grabbed a proton, forming 1 helium-4 nucleus, leaving 6 protons behind as hydrogen. The mass of the helium-4 nucleus is 4 nucleon masses, and the total mass of all 8 nucleons is 8 nucleon masses. So the mass fraction of helium-4 is 4 divided by 8, or 25% helium by mass, with the remaining 75% being hydrogen. This prediction, approximately 25% helium by mass and 75% hydrogen, is one of the crowning achievements of Big Bang nucleosynthesis theory, when astronomers measure the helium abundance in the most pristine, unprocessed regions of the universe. In metal-poor dwarf galaxies, where stellar nucleosynthesis has barely touched the primordial composition, they find a helium mass fraction of approximately 24 to 25%. The agreement between theory and observation is spectacular. But helium-4 was not the only product. Trace amounts of other nuclei were also synthesized. Deuterium itself survived in small quantities, roughly 1 nucleus for every 100,000 hydrogen nuclei. Helium-3 was produced at similar trace levels, and a tiny amount of lithium-7 was created, approximately 1 lithium nucleus for every 10 billion hydrogen nuclei. Why did nucleosynthesis stop at these light elements? Why didn't the universe continue building heavier and heavier nuclei? All the way up the periodic table, the answer lies in a pair of gaps in the landscape of nuclear stability, sometimes called the mass 5 gap and the mass 8 gap. There is no stable nucleus with 5 nucleons. Helium-5, which would consist of 2 protons and 3 neutrons, disintegrates almost instantly, in less than 10 to the negative 21 seconds. Lithium-5, with 3 protons and 2 neutrons, is equally unstable, and there is no stable nucleus with 8 nucleons either. Beryllium-8, consisting of 4 protons and 4 neutrons, falls apart into 2 helium-4 nuclei in roughly 10 to the negative 16 seconds. These gaps form an impassable barrier under Big Bang conditions. Helium-4, with 4 nucleons, is the last step on a smooth and easy reaction path. To reach the next stable nucleus beyond helium-4, you would need to somehow bridge one of these gaps. But helium-4 plus a proton gives mass 5, which is unstable. Helium-4 plus a neutron also gives mass 5, also unstable. Helium-4 plus helium-4 gives mass 8, also unstable. There is simply no two-body reaction involving helium-4 that can produce a stable, heavier nucleus. In stars, this bottleneck is overcome by a remarkable process called the triple alpha reaction, in which 3 helium-4 nuclei, also called alpha particles, come together almost simultaneously to form carbon-12. The process works because beryllium-8, although wildly unstable, exists for just long enough that a third helium-4 nucleus occasionally collides with it before it decays. This produces an excited state of carbon-12, which then drops to the ground state by emitting a gamma ray. The existence of this excited state at precisely the right energy level, a coincidence first predicted by the astrophysicist Fred Hoyle in 1953 as a necessary condition for carbon to exist in the universe at all, is one of the most remarkable fine-tunings in all of nuclear physics. But the triple alpha process requires extremely high densities sustained over long periods. In a stellar core, where temperatures exceed 100 million degrees and matter is compressed to thousands of times, the density of water, 3-body collisions happen often enough for the triple alpha process to proceed efficiently. This is partly thanks to a remarkable coincidence first identified by Fred Hoyle in 1954. Carbon-12 possesses an excited energy state, now called the Hoyle state, that sits at almost exactly the right energy to be resonantly produced from 3 helium-4 nuclei. Without this nuclear resonance, the triple alpha process would be far too slow to produce significant amounts of carbon, and the universe would be largely devoid of the element on which all known life is based. It is one of the most striking examples of a seemingly fine-tuned physical constant having profound consequences for the chemistry of the cosmos. But this resonance only helps at stellar densities and temperatures. In the rapidly expanding and cooling Big Bang universe, these conditions simply did not exist. The densities were dropping too fast, the window of opportunity too narrow, and the three-body collision rates were far too low. By the time the universe was about 20 minutes old, the temperature and density had dropped too far for any further fusion to occur. The window slammed shut. Nucleosynthesis was over, and the chemical inventory of the universe was essentially fixed. 75% hydrogen by mass, 25% helium, traces of deuterium and helium-3, a whisper of lithium-7, and nothing else. Every heavier element, every atom of carbon, nitrogen, oxygen, iron, gold, uranium. Every atom that is not hydrogen, deuterium, helium, or lithium would have to wait for stars to be born to live, and to die before it could exist. The periodic table beyond lithium is the product of stellar nucleosynthesis, not the Big Bang. But the Big Bang had done its job. It had taken pure energy and converted it into the raw material of the cosmos. The protons and neutrons that emerged from the quark-gluon plasma had been assembled in a furious 20-minute sprint into the nuclei of the lightest elements. Now those nuclei would drift through the expanding universe for hundreds of thousands of years, waiting for the next great transformation. The story of how we came to understand Big Bang nucleosynthesis is, in its own way, as remarkable as the physical processes themselves. It is a story of brilliant minds, missed opportunities, playful jokes, and one of the most unjust episodes in the history of scientific credit. It begins with George Gamow, a Soviet-born physicist who fled the USSR in the 1930s after multiple escape attempts, including a dramatic failed attempt to cross the Black Sea by kayak with his wife. Gamow was a polymath with an exuberant personality and an irrepressible sense of humor. He wrote popular science books filled with his own whimsical cartoons, loved practical jokes, and could not resist a good pun, even at the expense of his students' careers. He eventually settled at George Washington University in Washington, D.C., where he became a professor of physics and one of the leading figures in nuclear and theoretical physics. By the early 1940s, Gamow had become interested in a profound question. Could the abundances of the chemical elements be explained by nuclear reactions in the hot, dense conditions of the early universe? He envisioned a primordial state of matter, which he called Helium, borrowing a medieval word for primal substance, consisting of an incredibly hot and dense gas of neutrons. As this gas expanded and cooled, Gamow reasoned, the neutrons would decay into protons, and the resulting protons and neutrons would undergo nuclear reactions, building up the elements. To work out the details, Gamow needed help with the mathematical calculations, an area where he freely admitted his own limitations. He recruited a remarkably talented graduate student named Ralph Alpher. Alpher was the son of Jewish immigrants who had settled in Washington, D.C. He was not a person of great means or social standing, but he possessed a formidable intellect and a quiet determination to succeed. He attended George Washington University at night while working during the day. And by the mid-1940s, he had begun collaborating with Gamow on the nucleosynthesis problem. Alpher and Gamow spent roughly 3 years developing their theory. They calculated reaction rates, estimated initial temperatures and densities, and refined their model of how nuclear reactions would proceed in the first few minutes of the expanding universe. They imagined neutrons combining with protons to build deuterium, then heavier and heavier nuclei through successive neutron capture. The challenge was considerable. The early universe was a rapidly changing environment, with temperature and density dropping continuously as the expansion proceeded, and the calculations had to track many competing reactions simultaneously. It was an extraordinary intellectual adventure. They were, in effect, trying to reconstruct the first few minutes of cosmic history using nothing but physics and mathematics. By early 1948, the paper was ready for publication. It was titled The Origin of Chemical Elements, and it provided the first coherent framework for understanding how hydrogen and helium were produced in the Big Bang. The paper would appear in the Physical Review on April 1st, 1948, April Fool's Day, an appropriately mischievous date given what Gamow was about to do. Gamow realized that if the paper was authored by Alpher and Gamow, the byline would read Alpha and Gamma, corresponding to the first and third letters of the Greek alphabet. The irresistible temptation was to fill in the gap by adding the name of the eminent physicist Hans Bethe, whose name sounds like beta, the second Greek letter. Bethe had not contributed to the work, had no involvement in the calculations, and had not even read the manuscript before publication. But Gamow added his name anyway, over Alpher's strenuous and increasingly desperate objections, to create the famous Alpha Beta Gamma byline. Gamow was delighted with his pun. Bethe was amused and reportedly happy to have his name attached to what he recognized as an important paper, even though he had done none of the work. But for Alpher, the joke was a professional catastrophe. The public and the physics community naturally assumed that the famous Gamow and Bethe, both towering figures in physics, had done the heavy intellectual lifting, and the young, unknown Alpher was merely a minor assistant. The Alpha Beta Gamma joke became one of the most famous stories in 20th century physics, and it has been retold countless times with warmth and humor. But it must be said that it came at a real cost to Alpher, who spent much of his subsequent career fighting for recognition of his contributions. Alpher's thesis defense drew an audience of 300 people, an extraordinary turnout for a doctoral examination. Spilling out of the lecture hall and into the corridors, the Washington Post reported the results under the attention-grabbing headline, "World Began in 5 Minutes." The story was picked up nationally, and for a brief moment, Alpher was famous, but the fame was fleeting, and in many ways it was stolen from him. The public assumed the paper was primarily the work of the famous Gamow and Bethe. Alpher, the unknown graduate student who had actually done the calculations, was treated as a footnote in his own work. It was an injustice that would shadow his career. After completing his doctorate, Alpher found that an academic career was largely closed to him, whether this was due to the perception that the alpha beta gamma work was really gammos and beths, or to the anti-Semitism that still pervaded parts of American academia in the late 1940s, or simply to the misfortune of being a young, unknown physicist in a field dominated by giants. The result was the same. Alpher eventually took a position at the General Electric Research Laboratory in Schenectady, New York, where he did excellent work in applied physics, but was largely cut off from the academic cosmology community. Before leaving academia, however, Alpher and his colleague, Robert Herman, who, as Gamow jokingly lamented, refused to change his surname to Delter to continue the Greek alphabet sequence, made one more extraordinary contribution. Working together on early universe physics, they published a series of papers in 1948 and 1949 that included a prediction so far ahead of its time that the physics community simply did not know what to do with it. They calculated that the cooling radiation left over from the hot Big Bang should still permeate the universe today. By tracing the expansion and cooling of the universe from its initial hot state to the present day, they estimated that this relic radiation would have a temperature of roughly 5 degrees above absolute zero. This was the first prediction of what we now call the cosmic microwave background radiation, arguably the single most important prediction in the history of cosmology. The prediction was largely ignored. Part of the problem was that Alpher and Herman did not have the stature to command attention. Part of it was that the technology to detect such faint microwave radiation did not yet exist, or at least was not recognized as existing. And part of it was that cosmology itself was still a somewhat disreputable field in the 1940s and 50s, not yet taken as seriously as particle physics or condensed matter research. The prediction sat in the journals, gathering dust, while the radiation it described bathed the entire universe in a faint, invisible glow. Tragically, their prediction was largely ignored by the wider physics community. The observational tools to test it did not yet exist, and the physics establishment, focused on the rapid developments in quantum electrodynamics and nuclear physics, paid little attention to cosmology. The cosmic microwave background would not be detected for another 16 years, and when it was discovered, the credit would go elsewhere. The alpha beta gamma paper also contained significant errors. Alpher and Gamow had envisioned a process of successive neutron capture that would build up all the elements, not just the lightest ones. This could not work because of the mass 5 and mass 8 gaps. The heavier elements, it would turn out, are built in stars, not in the Big Bang. This was demonstrated in a landmark 1957 paper by Margaret Burbidge, Jeffrey Burbidge, William Fowler, and Fred Hoyle, often referred to as the B²FH paper, which laid out the theory of stellar nucleosynthesis in magnificent detail. Margaret Burbidge, the lead author and primary observer for the project, would live to the age of 100 and is remembered as one of the most influential astronomers of the 20th century. But what the alpha beta gamma theory did get right, and magnificently so, was the production of hydrogen and helium. Together, These two elements account for more than 99% of all the ordinary matter in the cosmos, and their observed abundances match the predictions of Big Bang nucleosynthesis with impressive precision. The theory was refined and improved over the following decades, with contributions from Jim Peebles, who in the mid-1960s used the newly measured temperature of the cosmic microwave background to perform more precise nucleosynthesis calculations, and by Robert Waggoner, William Fowler, and Fred Hoyle, who expanded the network of nuclear reactions, considered and produced detailed numerical predictions. Each refinement brought the predictions into closer agreement with observations. The predictions of Big Bang nucleosynthesis are extraordinary in their specificity. They tell us, given only a single input parameter, the density of baryonic matter in the universe, exactly how much hydrogen, helium, deuterium, and lithium should exist. And over the decades, observations have confirmed these predictions with remarkable accuracy. But how do we actually measure the primordial abundances? The challenge is formidable. Stars have been fusing hydrogen into helium and producing heavier elements for billions of years. Supernovae have enriched the interstellar medium with metals. Stellar winds have redistributed material throughout galaxies. The raw, primordial composition of the universe has been contaminated by 13.8 billion years of stellar nucleosynthesis in most places. To get at the original abundances, astronomers must look for environments where this contamination is minimal, cosmic pristine environments, where the elemental composition has been barely touched since the Big Bang. For primordial helium-4, the method involves studying the most chemically primitive galaxies we can find, specifically metal-poor dwarf galaxies. These are small, faint galaxies with very low abundances of elements heavier than helium, which astronomers call metals because they have undergone relatively little star formation over their histories. Their elemental composition is closer to the primordial mixture. Astronomers measure the helium recombination emission lines in ionized hydrogen, HII, regions within these galaxies, where young, hot stars have ionized the surrounding gas. By carefully analyzing the relative intensities of these emission lines and extrapolating to zero metallicity, eliminating the contribution from stellar processing, astronomers can estimate the primordial helium abundance. The result consistently lands at approximately 24 to 25% by mass, in excellent agreement with the Big Bang prediction. For primordial deuterium, the measurement is even more dramatic and in many ways more precise. Deuterium is extremely fragile. It is easily destroyed in stellar interiors, where temperatures are more than sufficient to break apart its weakly bound nucleus, and it is never produced in significant quantities by stars. So any deuterium we observe today is almost entirely primordial, a direct relic of the Big Bang. The best measurements come from high redshift gas clouds, called Lyman alpha absorption systems, that happen to lie along the line of sight to distant quasars. The brilliant light from the quasar passes through the intervening gas cloud, and certain wavelengths are absorbed by the deuterium atoms in the cloud. Because deuterium is slightly heavier than ordinary hydrogen, its absorption lines are shifted by a tiny amount from the hydrogen lines, allowing astronomers to separately measure the deuterium abundance. By carefully analyzing these absorption features, astronomers can determine the deuterium to hydrogen ratio with extraordinary precision. The observed value, roughly 2.5 parts per 100,000, matches the Big Bang prediction for the independently measured baryon density with impressive accuracy. The confirmation of these predictions provided powerful evidence for the Big Bang model. But the most dramatic piece of evidence came not from measuring elemental abundances, but from detecting the radiation itself, the afterglow of the Big Bang, the relic photons that had been filling the universe since the first fraction of a second. In 1964, at the Bell Telephone Laboratories facility in Holmdel, New Jersey, two radio astronomers named Arno Penzias and Robert Wilson were using a large, horn-shaped antenna, originally built for satellite communication experiments with the ECHO project, to study radio emissions from the Milky Way galaxy. They encountered a persistent, low-level hiss of microwave radiation that they could not eliminate, no matter what they did. It came from every direction. It did not vary with the time of day or the season or the position of the antenna. They checked their equipment exhaustively. They rebuilt connections. They even climbed inside the 20-foot horn antenna and carefully removed a layer of pigeon droppings that had accumulated inside, suspecting that the bird excrement might be the source of the unwanted noise. The noise remained. Penzias and Wilson were baffled. They knew the signal was not coming from the sun, or from the Milky Way, or from any known astronomical source. It appeared to be a genuine, isotropic, uniform background radiation, arriving from every direction with equal intensity, at a temperature they measured as approximately 3.5 degrees above absolute zero. Eventually, through a chain of fortuitous connections, Penzias learned that a team at nearby Princeton University, led by Robert Dick, along with Jim Peebles, Peter Roll, and David Wilkinson, had been working on precisely this prediction. They had independently calculated that the Big Bang should have left behind a relic background of thermal radiation. And they were in the process of building an antenna to search for it. When Dick heard about the Bell Labs measurement, he famously turned to his colleagues and said something to the effect of, "Boys, we've been scooped." The two groups published companion papers in the Astrophysical Journal in 1965. Penzias and Wilson described their measurement with careful scientific restraint, noting only that they had detected an excess antenna temperature of roughly 3.5 degrees that they could not account for. Dick and his colleagues provided the cosmological interpretation, explaining that this signal was consistent with the cooled remnant of radiation from the hot, early universe. The discovery transformed cosmology overnight. The steady-state theory, championed by Fred Hoyle and others, which held that the universe had no beginning and was instead in a state of continuous creation, was dealt a fatal blow. The cosmic microwave background was exactly what the Big Bang theory predicted, and exactly what the steady-state theory could not explain. Penzias and Wilson shared the 1978 Nobel Prize in Physics for their discovery, though many felt that Dick and his Princeton colleagues, who had provided the theoretical framework, deserved a share of the recognition. For Ralph Alpher and Robert Herman, the discovery was bittersweet. They had predicted the existence of this background radiation 16 years earlier, in 1948 and 1949, and they had been ignored. Their prediction, published in papers that received little attention at the time, had foreseen the existence of relic radiation at a temperature of approximately 5 degrees, close to the actual measured value. Yet when the CMB was finally discovered, its contribution was initially overlooked. Alpher, in particular, felt the injustice deeply. He had spent years working on the problem, had been overshadowed by Gamo's alpha-beta-gamma joke, and now saw the confirming observation credited to others, while his prediction languished in obscurity. It would take decades before the contributions of Alpher and Hermann were properly recognized by the scientific community. Alpher passed away in 2007, having lived long enough to see some measure of acknowledgement, but never receiving the Nobel Prize that many believed he deserved. The cosmic microwave background, as it came to be known, was the cooled remnant of the radiation that had filled the universe since the earliest moments. The photons that Penzias and Wilson detected had last interacted with matter roughly 380,000 years after the Big Bang, at the moment when the universe cooled enough for atoms to form, but they carried information about conditions at far earlier times, including the era of nucleosynthesis. Subsequent missions, COBE in the early 1990s, WMAP in the 2000s, and Planck in the 2010s, measured the cosmic microwave background with extraordinary precision. NASA's Cosmic Background Explorer, or COBE, launched in 1989, confirmed that the CMB had a nearly perfect blackbody spectrum, the most precise blackbody ever measured in nature, and detected, for the first time, the tiny temperature fluctuations across the sky that had been predicted by inflationary theory. The COBE team's principal investigator, John Mather, and the lead scientist on the anisotropy measurement, George Smoot, shared the 2006 Nobel Prize in Physics for this work. NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped these fluctuations in far greater detail, providing the first precision measurements of key cosmological parameters. And the European Space Agency's Planck satellite, launched in 2009, achieved higher resolution and sensitivity, measuring the CMB temperature to be 2.725 degrees above absolute zero, with fluctuations at the level of a few tens of millionths of a degree. The tiny temperature fluctuations in the CMB, variations of only a few parts in 100,000, encoded a wealth of information about the early universe, including the density of baryonic matter. This baryon density, measured independently from the CMB, could then be fed into the nucleosynthesis equations to predict the primordial abundances. The fact that these predictions matched the independently observed abundances was a triumph of consistency. Two completely different observations, the CMB and the elemental abundances, pointed to the same answer. It was, in the words of many cosmologists, one of the most beautiful confirmations in the history of science. But the story of Big Bang nucleosynthesis is not one of perfect agreement. There is a discrepancy, a nagging puzzle that has resisted resolution for decades. It involves the lightest metal in the periodic table, lithium. Big Bang nucleosynthesis theory predicts that the universe should contain a specific amount of lithium-7, one of the two stable isotopes of lithium. The predicted abundance, calculated using the baryon density determined from the cosmic microwave background, is approximately 4 to 5 lithium-7 nuclei for every 10 billion hydrogen nuclei. This is a tiny amount, but it is measurable. The problem is that when astronomers look at the oldest, most chemically primitive stars in our galaxy, the so-called population 2 stars that formed when the galaxy was young and had not yet been enriched by many generations of stellar nucleosynthesis, they find significantly less lithium-7 than predicted. The observed abundance is roughly a factor of 3 lower than the theoretical prediction. Stars on the so-called Spite Plateau, named after the French astronomers Francois and Monique Spite, who first characterized this pattern in 1982, show a remarkably uniform lithium abundance that falls well below the Big Bang prediction. This is the cosmological lithium problem, and it is one of the most persistent, unresolved tensions in modern cosmology. The discrepancy is significant, a factor of roughly 2 to 4 depending on which measurements and models are used, and it stubbornly refuses to go away. Multiple explanations have been proposed, and the search for a solution has become one of the more active areas of research at the intersection of nuclear physics, stellar astrophysics, and cosmology. Perhaps the lithium is being destroyed inside the stars themselves, mixed by convective currents down into hotter layers where it is broken apart. Lithium is indeed fragile, easily destroyed at temperatures above about 2.5 million degrees, temperatures that exist in the outer layers of some stars. Processes like turbulent mixing, atomic diffusion, and gravitational settling could carry surface lithium down to hotter regions where it would be burned. But detailed stellar models have struggled to reproduce the exact amount of depletion needed to resolve the discrepancy without also depleting other elements in ways that would contradict observations. The uniformity of the Spite Plateau is also puzzling from this perspective. If stellar processes were responsible, one might expect more variation from star to star, depending on the details of each star's internal mixing. Perhaps the nuclear reaction rates used in the Big Bang calculations are slightly wrong. Lithium-7 is not produced directly in the Big Bang. Instead, beryllium-7 is produced during nucleosynthesis through the reaction of helium-3 plus helium-4, and beryllium-7 later decays into lithium-7 by electron capture, with a half-life of about 53 days. If the reaction that produces beryllium-7 were slightly less efficient than we think, or if some competing reaction that destroys beryllium-7, such as neutron capture on beryllium-7, were slightly more efficient, the predicted abundance could be reduced. Experimentalists have been carefully measuring the relevant nuclear cross-sections in laboratories around the world, and while small adjustments have been made, none have been large enough to solve the problem. Perhaps the solution lies in new physics beyond the standard model. Some theorists have proposed that decaying or annihilating dark matter particles could have injected additional energy into the primordial plasma during or just after nucleosynthesis, disrupting the delicate chain of reactions that produces beryllium-7. Others have suggested that the velocities of particles in the Big Bang plasma might not follow the standard statistical distribution, and that alternative statistical frameworks could alter the predicted abundances. In 2017, a team led by Suking Hu at the Chinese Academy of Sciences proposed that using non-extensive statistics, a generalization of the classical Maxwell-Boltzmann distribution, originally developed by the Brazilian physicist Constantino Tsalles, could simultaneously reproduce the observed abundances of deuterium, helium, and lithium. The idea is that the extreme, rapidly evolving conditions of the Big Bang plasma might produce slight deviations from perfect thermal equilibrium that are not captured by classical statistics. This is an intriguing possibility, but it remains speculative and has not been independently confirmed. The lithium problem serves as a humbling reminder that even our most successful theories can harbor unresolved tensions. Big Bang nucleosynthesis is spectacularly successful for hydrogen, deuterium, helium-3, and helium-4. But for lithium, something is not quite right, and no one yet knows what. It could be a mundane astrophysical effect, hidden in the complex interiors of ancient stars. Or it could be a signpost pointing toward entirely new physics, waiting to be discovered. History teaches us that discrepancies between theory and observation, when they persist and resist easy explanation, sometimes turn out to be the cracks through which revolutionary new understanding emerges. After nucleosynthesis ended, the universe entered a long, quiet era. The nuclear reactions were over. The elemental composition was fixed, but the universe was still incredibly hot, tens of millions of degrees, and it would remain that way for a very long time. The matter in the cosmos was a plasma, a soup of positively charged atomic nuclei, mostly hydrogen and helium, and negatively charged electrons. These were not yet atoms. The electrons were free, unbound, zipping around at tremendous speeds. And because free electrons are extraordinarily effective at scattering photons, through a process called Thomson scattering, the universe was opaque. Light could not travel in a straight line. Every photon that was emitted was almost immediately deflected by a free electron, then deflected again and again, 1 trillion times over. The universe was, in effect, a dense, luminous fog. Imagine being suspended inside this fog. You would not be able to see your hand in front of your face, because no photon could travel more than a short distance before being scattered in a random direction. The universe was flooded with light, blazing with radiation at every point, but that light carried no information. It was a bath of randomized photons, bouncing ceaselessly off the free electrons, unable to stream freely in any direction. The universe was simultaneously as bright as a stellar furnace and as opaque as a solid wall. This state of affairs persisted for approximately 380,000 years. During all that time, the universe was expanding and cooling, the temperature dropping steadily, century by century, millennium by millennium. But the temperature remained above the threshold at which electrons could be captured by nuclei to form neutral atoms. The ionization energy of hydrogen is 13.6 electron volts, and you might naively expect atoms to form when the universe cools to a temperature corresponding to that energy. But that naive expectation would be wrong. The reason is the same one that created the deuterium bottleneck. There are far more photons than atoms. The photon-to-baryon ratio, roughly 1 billion to 1, meant that even when the average photon energy drops below 13.6 electron volts. The high-energy tail of the photon distribution still contains enough energetic photons to rip electrons away from newly formed hydrogen atoms almost as fast as they can be captured. The universe has to cool much further, to a temperature of approximately 3,000 degrees, roughly corresponding to an energy of only about 0.3 electron volts, before the rate of ionization drops low enough for atoms to survive. This is about 45 times lower than the naive estimate. And the reason is the same billion-to-1 photon ratio that delayed nucleosynthesis at the deuterium bottleneck. This happened at a redshift of approximately 1100, meaning the universe has expanded by a factor of roughly 1100 since that time. At that moment, about 378,000 years after the Big Bang, the free electrons finally combined with the hydrogen and helium nuclei to form neutral atoms. This process is called recombination, despite the fact that the electrons and nuclei had never been combined before. A misnomer that has been the source of gentle amusement in the cosmology community for decades. Recombination was not instantaneous. It was a gradual process that unfolded over a span of roughly 60,000 years. Helium, with its higher ionization energy, recombined first, capturing its electrons at slightly higher temperatures. Then, as the temperature continued to drop, hydrogen followed. The process was not a simple cascade of electron capture. Each time a hydrogen atom captured an electron directly into its ground state, it emitted a photon with exactly 13.6 electron volts of energy, more than enough to ionize another nearby hydrogen atom. So recombination could not proceed by direct capture to the ground state. Instead, electrons had to be captured into excited states of hydrogen, then cascaded down to the ground state through intermediate energy levels, emitting photons at each step that were not quite energetic enough to ionize other atoms. This multi-step process, first worked out in detail by Jim Peebles in 1968, and independently by Yakov Zeldovich and Rashid Sunyaev in the Soviet Union around the same time, was slower and more complicated than simple capture. But it worked. Atom by atom, the hydrogen in the universe became neutral. As neutral atoms formed, the scattering of photons by free electrons dropped precipitously. The fog cleared. For the first time in the history of the universe, light could travel freely across vast distances. This moment is called photon decoupling, and it is the origin of the cosmic microwave background. The photons that were released at decoupling have been traveling through space ever since, gradually cooling as the universe expanded, stretching from visible light to infrared to microwaves. Today, they form a nearly perfect blackbody spectrum at a temperature of 2.725 degrees above absolute zero, filling the entire sky with a faint, uniform glow. The cosmic microwave background is, in essence, a photograph of the universe at the moment of recombination. It shows us the cosmos as it was 380,000 years after the Big Bang, a time when the universe was roughly 1,000 times smaller and 1,000 times hotter than it is today. The tiny temperature fluctuations in the CMB, first detected by the COBE satellite in 1992, represent the density variations in the primordial plasma, slightly denser regions that would eventually collapse under gravity to form galaxies, and slightly thinner regions that would become the great cosmic voids. But recombination also marked the moment when atoms, true atoms, existed for the first time. Hydrogen atoms have 1 proton and 1 electron. Helium atoms have 2 protons, 2 neutrons, and 2 electrons. Traces of deuterium and lithium. These were the first stable, electrically neutral structures in the history of the universe. Simple, quiet, unremarkable. But they were something genuinely new. For 380,000 years, the universe had been a plasma. Now it was a gas. And that gas, free at last from the relentless scattering of photons, could begin to respond to another force that had been patiently waiting in the background all along: gravity. After recombination, the universe entered a period that astronomers call the cosmic dark ages. There were no stars, there were no galaxies, no quasars, no supernovae, no points of light anywhere in the vastness of space. The only electromagnetic radiation was the cooling cosmic microwave background, its peak wavelength redshifting steadily from visible orange-red light toward infrared, and then into the microwave range, and the occasional faint 21-centimeter emission from neutral hydrogen atoms undergoing spin-flip transitions. The universe was dark, cold, and quiet. Profoundly, incomprehensibly quiet. If you could have stood in the middle of this universe, which of course you could not have, because there were no solid surfaces to stand on and no breathable atmosphere and no warmth, you would have seen nothing, absolute blackness in every direction. No pinpricks of starlight, no Milky Way, no constellations, just an infinite, cooling darkness filled with invisible hydrogen and helium gas, expanding silently outward for hundreds of millions of years. Nothing dramatic happened. The universe simply expanded, cooled, and waited. And yet in that darkness, in that patient, silent waiting, something was happening. Something slow and inexorable. Gravity, the weakest of the 4 fundamental forces, but the only one that never gives up, was doing its quiet work. The tiny density fluctuations that had been frozen into the fabric of space by inflation, preserved through the eras of nucleosynthesis and recombination, were growing. Regions that were slightly denser than average had slightly stronger gravitational pulls. And so, they attracted more matter from their surroundings, which made them denser still, which increased their gravitational pull further. This is the gravitational instability that James Jeans first described mathematically in the early 20th century. And it operates on all scales, from the sizes of individual gas clouds to the spans of galaxy superclusters. Dark matter played a crucial role. Because dark matter does not interact with photons, it was not subject to the radiation pressure that had prevented ordinary matter from clumping before recombination, while the baryonic plasma was locked in a tug-of-war between gravity, which tried to pull it together, and radiation pressure, which pushed it apart, creating the acoustic oscillations that are visible as peaks in the CMB power spectrum. The dark matter was free to collapse under gravity without opposition. By the time of recombination, dark matter had already formed a network of filaments and clumps, an invisible scaffolding that we now call the cosmic web. When the ordinary matter, the hydrogen and helium atoms, was finally released from the grip of the photons at recombination. It fell into the gravitational wells that the dark matter had already prepared. This process took time, hundreds of millions of years of slow accumulation. Gas flowing along dark matter filaments, pooling in the densest knots, heating up as it fell and compressed, and somewhere around 100 to 200 million years after the Big Bang, in the deepest and most massive of these gravitational wells, the gas reached temperatures and densities sufficient for nuclear fusion to ignite, but it was not featureless. Those tiny density fluctuations, the seeds planted by inflation and preserved through nucleosynthesis and recombination, were slowly growing. Gravity, the weakest of the four fundamental forces, but the most patient, was doing its work. Dark matter, which does not interact with light and therefore was not affected by the photon pressure that had kept ordinary matter from clumping before recombination, had already begun to accumulate in the denser regions, forming the invisible scaffolding of the cosmic web. These dark matter halos grew steadily, merging with one another, building larger and larger gravitational wells. And ordinary matter, the hydrogen and helium atoms newly freed from the photon fog, began to fall into these dark matter structures, accumulating in the gravitational wells like water pooling in valleys. As the gas collected, it grew denser. As it grew denser, it heated up through compression. And eventually, somewhere in the universe, roughly 100 to 200 million years after the Big Bang, a cloud of primordial hydrogen and helium gas collapsed under its own gravity to the point where the temperatures and pressures at its core were sufficient to ignite nuclear fusion. The first star was born. These were the population 3 stars, theoretical objects never yet directly observed, believed to have been enormous and short-lived, perhaps hundreds of times the mass of our sun. They burned hot and blue and furiously, their lifetimes measured in millions of years rather than the billions that smaller stars enjoy. In their cores, they fused hydrogen into helium, and then helium into carbon through the triple alpha process that had been impossible during the Big Bang, and carbon into oxygen, neon, and silicon, and all the way up to iron. And when they died, in catastrophic supernova explosions of extraordinary violence, they scattered those newly forged elements into the surrounding gas, enriching it with the materials that would eventually form rocky planets, liquid water, organic molecules, and life. This was stellar nucleosynthesis, the second great wave of element building, and it would eventually produce every element in the periodic table from carbon all the way up to uranium and beyond. The first stars also flooded the universe with ultraviolet radiation, torrents of energetic photons pouring outward from their blazing surfaces and slamming into the surrounding neutral hydrogen gas. This ultraviolet light was energetic enough to strip electrons from hydrogen atoms, reionizing gas that had been neutral since the epoch of recombination. Around each of the first stars, a bubble of ionized gas expanded outward, growing larger as more radiation poured out, as more stars formed, and as the first small galaxies assembled from merging clusters of stars. These ionized bubbles grew and merged, like holes in Swiss cheese, gradually connecting until the cheese was more whole than solid. This process is called cosmic reionization, and it unfolded over a span of several hundred million years. from roughly 200 million years after the Big Bang to perhaps 700 million years or more. Reionization is one of the great frontiers of observational cosmology. The James Webb Space Telescope, launched in late 2021, was designed in part to observe the earliest galaxies and study the epoch of reionization in unprecedented detail. Its infrared instruments can detect light from galaxies that formed when the universe was only a few hundred million years old. Galaxies whose light has been traveling toward us for more than 13 billion years, stretched by the expansion of the universe from ultraviolet and visible wavelengths into the infrared. These observations are beginning to fill in one of the last major gaps in our understanding of cosmic history. The period between the formation of the first atoms and the emergence of the galaxy-filled universe we see today. The epoch of reionization marks the end of the cosmic dark ages and the beginning of the universe as we recognize it. A cosmos of galaxies and galaxy clusters, of quasars and supernovae, of the great cosmic web of filaments and voids that stretches across billions of light years. But none of that could have happened without the foundation laid in the first 20 minutes. The hydrogen that fuels the stars, the helium that makes up a quarter of their mass, the deuterium that serves as a stepping stone in stellar fusion chains. All of it was created in those first frantic minutes after the Big Bang, when the universe was an expanding fireball, just cool enough for nuclear reactions to proceed, and just hot enough for them to succeed. Let us pause here and reflect on the sheer improbability and precision of what we have described. The chemical composition of the universe, the recipe of 75% hydrogen and 25% helium that governs everything from stellar evolution to the formation of planets, is not an accident or a coincidence. It is the product of a specific sequence of physical processes, each one sensitively dependent on the values of fundamental constants. Consider how things might have gone differently if the neutron had been slightly heavier relative to the proton. The neutron-to-proton ratio at freeze-out would have been different, and the universe might have produced far more or far less helium. If the neutron were lighter than the proton instead of slightly heavier, then it would be the proton that decayed, and the universe would be filled with neutrons instead of hydrogen. A radically different cosmos with no chemistry as we know it. If the strong nuclear force were slightly stronger, the deuterium nucleus would be more tightly bound, and the deuterium bottleneck would break earlier when more neutrons were still available, producing more helium. If the strong force were slightly weaker, deuterium might not be bound at all, and nucleosynthesis beyond hydrogen would never occur. If the expansion rate of the universe had been slightly faster, the temperature would have dropped through the nucleosynthesis window more quickly, leaving less time for reactions and producing less helium. If it had been slightly slower, more helium would have been produced, potentially leaving too little hydrogen for the long-lived stars that are needed to sustain stable planetary systems for billions of years. If the matter-antimatter asymmetry had been precisely zero, as symmetry would suggest, the annihilation would have been complete, and the universe would contain no matter at all, just a cooling sea of photons expanding into emptiness forever. If the asymmetry had been much larger, the universe would be denser, and its thermal history would be different, potentially altering the neutron-to-proton ratio, the nucleosynthesis yields, and the entire course of cosmic evolution. Every step in the chain, from the Planck epoch to recombination, was governed by the precise values of fundamental constants and the exact laws of physics. And the result was a universe with exactly the right composition to produce stars, planets, chemistry, and eventually life. This is not evidence of supernatural design. It is evidence of the extraordinary power and precision of the physical laws that govern our cosmos, and of the sensitivity of the universe's evolution to the values of its fundamental parameters. Every hydrogen atom in the water you drink, in the organic molecules of your cells, in the vast molecular clouds between the stars, was forged in the first seconds to minutes of cosmic history. Every helium atom that fills a party balloon, that makes your voice go squeaky when you inhale it, that fuses in the core of the sun to produce the light that sustains life on Earth, was assembled in the primordial nucleosynthesis of the Big Bang. These atoms are among the oldest objects in the universe. They predate every star, every galaxy, every planet. They are, in a real and physical sense, the original matter of creation, and they came from energy, pure, undifferentiated, blinding energy. The universe began as a formless blaze of radiation, inconceivably hot, infinitely dense, containing no atoms, no nuclei, no particles as we know them. Through a sequence of phase transitions, symmetry breakings, annihilations, decouplings, and nuclear reactions, each governed by the precise laws of physics, that energy was gradually shaped, cooled, and condensed into the matter we see today. It was not a gentle process. It was violent, chaotic, and breathtakingly fast. But it was also, in its own way, exquisitely precise. The laws of physics acted as a filter, selecting which particles would survive, which nuclei would form, which elements would dominate the cosmos. And the result, written in the abundances of hydrogen and helium that pervade the universe, is one of the clearest and most beautiful confirmations of our understanding of nature. Consider the journey we have taken. We began at the Planck epoch, a time so early that physics itself cannot describe it. We watched gravity separate from the other forces. We saw inflation stretch the universe by a factor of 10 to the 26th in a fraction of a second, seeding the quantum fluctuations that would become galaxies. We witnessed the Higgs field switch on, giving mass to the fundamental particles. We saw the quark-gluon plasma, the most perfect liquid in nature, crystallize into protons and neutrons. We watched matter and antimatter annihilate in a cataclysm that left only one particle in a billion standing. We saw the neutrinos decouple and stream away into the void. We waded through the deuterium bottleneck. We watched the frantic sprint of nucleosynthesis, forging helium, deuterium, and lithium in just 17 minutes. We followed the universe through 380,000 years of slow cooling, until the fog cleared and the first atoms formed. And we looked ahead to the dark ages and the birth of the first stars, and the beginning of the long process of stellar nucleosynthesis that would eventually produce every element in the periodic table. All of this, every step, was set in motion by the initial conditions of the Big Bang and governed by the laws of physics. And all of it left traces that we can detect and measure today, from the proportions of hydrogen and helium in distant gas, clouds to the faint microwave glow that fills every corner of the sky. We are, all of us, made of atoms that trace their lineage back to those first moments. The hydrogen in your body was once part of the primordial plasma, drifting through a universe that was still opaque, waiting for electrons to come and form the first neutral atoms. The carbon, oxygen, and iron in your body were forged later, in the hearts of massive stars that exploded and seeded the cosmos with heavier elements. But it was the hydrogen and helium of the Big Bang that made those stars possible in the first place. Without the primordial fuel, the universe would be a dark, empty, featureless expanse. No stars, no light, no us. The first atoms were not spectacular objects. They were simple, humble, unremarkable. A single proton with a single electron. 2 protons, 2 neutrons, 2 electrons. The most basic building blocks imaginable. But from these humble beginnings, everything followed. Gravity gathered them into clouds. Clouds collapsed into stars. Stars fused them into heavier elements. Those elements formed planets, oceans, atmospheres, and eventually, on at least one small rocky world orbiting an ordinary yellow star in an unremarkable spiral galaxy, they assembled themselves into structures complex enough to look up at the night sky and wonder where they came from. The answer is right there, in the proportions of hydrogen and helium that fill the cosmos. 75% hydrogen, 25% helium, a trace of deuterium, a whisper of lithium. That is the recipe. That is the primordial composition. And it tells us, with extraordinary clarity, that we live in a universe that began in fire and slowly, over billions of years, cooled into the rich, complex, beautiful cosmos we see today. The first atoms were simple, but they were the beginning of everything. Consider the journey we have just traced from the Planck epoch, a moment so brief and so extreme that our best theories of physics cannot describe it, through the separation of forces and the fury of inflation, through the strange and beautiful quark-gluon plasma, and the catastrophic annihilation of matter and antimatter, through the quiet departure of the neutrinos and the ticking clock of neutron decay, through the deuterium bottleneck and the 20-minute nuclear forge that produced the primordial elements, through hundreds of thousands of years of patient waiting as the plasma cooled and thinned, all the way to the moment when the fog cleared and the first true atoms drifted silently through an expanding, darkening cosmos. Each step was governed by specific physical laws. The strong force binding quarks into protons, the weak force setting the neutron-to-proton ratio, electromagnetism scattering photons off free electrons, and gravity slowly gathering matter into the seeds of structure. Each step was contingent on what came before, and each step set the conditions for what would come after. If any of these steps had been even slightly different, if the matter-antimatter asymmetry had been zero, or if the neutron had been slightly heavier or slightly lighter, or if the deuterium binding energy had been a little weaker, or if the expansion rate had been a little faster or a little slower, the outcome would have been a profoundly different universe. Perhaps a universe with no helium, where stars would burn differently and produce different elements. Perhaps a universe with too much helium, where hydrogen would be scarce and long-lived. Sun-like stars could not form. Perhaps a universe with no matter at all, just an empty, expanding void of cooling light. the universe we inhabit, with its particular chemical recipe. It's 75% hydrogen and 25% helium. Its traces of deuterium and its whisper of lithium is the product of an extraordinarily specific sequence of events, each one playing out according to the laws of physics as we understand them. And the result is a cosmos that is, against all odds, capable of producing stars, planets, chemistry, biology, and minds that can look back across 13.8 billion years and reconstruct the story of their own origins. That, perhaps, is the most astonishing thing of all. Not that the universe made hydrogen and helium. Not that it did so in 20 minutes, starting from pure energy, but billions of years later. Some of those atoms would arrange themselves into configurations complex enough to understand how they were made. The hydrogen in your body knows nothing of the Big Bang. It is just a proton and an electron, bound together by the electromagnetic force, following the laws of quantum mechanics as it has done for nearly 14 billion years. But you, assembled from those ancient atoms, can look up at the night sky, observe the cosmic microwave background, measure the helium abundance in distant galaxies, calculate the nuclear reaction rates, and piece together the entire story. The atoms are simple. The story they tell is not. And that story is still being written. The lithium problem remains unsolved. The origin of the matter-antimatter asymmetry is unknown. The nature of dark matter, which played such a crucial role in gathering the first atoms into structures, is a mystery. The theory of quantum gravity, which would allow us to push our understanding all the way back to the Planck epoch, and perhaps beyond, does not yet exist. Every answer we have found has opened new questions, and every new observation has deepened the mystery, even as it has illuminated the cosmos. But we know this much. The universe began in fire. It cooled. Energy became matter. Matter became atoms. Atoms became stars, and stars became everything else. And it all started in those first frantic 20 minutes with the simplest elements imaginable, forged from nothing but light and heat in the expanding fireball of the Big Bang, hydrogen and helium. The first atoms, the foundation of everything. You have been watching the entire history of the universe. Don't forget to like and subscribe, and leave us a comment to tell us what you think. Thanks for watching, and we will see you next time.